All right. Good afternoon, everyone. Today is January 5th. This is Astro 10 Intersection online course. And today, brief review. If this is the first time you are opening any communication from me, as soon as you enter the course, look on your right hand side. And I know Alexander is not seeing what I'm showing, but I'm taping this. On the right hand side, you have all the to-dos that you have to work on. There is a discussion going on. In fact, the discussion one is the one you should be working now, but you can start the number 2 as well. And there are some extra credits and homework chapter 1 and 2, and these are supposed to close on Saturday. In fact, chapter 2 is the one that I'm starting today, and but it's going to be closing on Saturday. So and a bunch of extra credits. So basically, once you pay attention to that, you can go to modules. And January 5th, we are starting chapter 2. So what I'd like to do is to go over the basic subject of chapter 2 and chapter 4 tomorrow. So chapter 4 tomorrow, chapter 2 today. But basically, I'm kind of opening up the subject on it. It's a lot of information, and it has to do with the night sky. So for Alexandra, let me share the screen. And there you go. You wonder why it's not appearing. Oh, there you go. All right, so basically, chapter 2 is introduce the concept of celestial sphere. So celestial sphere is not a real thing, is an hypothetical sphere that was conceived in the past, and right now we still use because it helps to identify position of objects in the sky. It it's it's a way to add and to create coordinate systems so that we can locate objects. And we are not going to detail those coordinate systems and work on it, but it's good for you to know this concept. So basically, if you look at this picture over here, in fact, what I would do, this PowerPoint is small. Let's see if I can expand this. So I stop sharing, and then I have to manage all these different windows and not being that efficient. I would like to share the entire optimized full screen video, share computer sound. Yeah, I would prefer if I could share my entire screen, not just one of the screens available. But anyway, um, so if you look at this comment, annotate. Oh, there you go. So no matter where you are, I mean, right now you might be in your room, or you might be looking at a screen, your cell phone. Just stop looking at the screen and then look around you. I mean, in a room. But if you look around you, if you could get rid of the walls or trees or whatever is around you in such a way that you could look without impedance all the way to as far away as you can. So imagine you are on the top of a cliff, and then in an island, right? So you are in a cliff in an island, you are in the very top, and then you look around, and then what you see is water and the sky meeting the water very far away. So that point, the dividing line between the sky and the water, is what we call horizon, and that's what you have right here. So this is your horizon. Um, And the horizon is not a circle, by the way, but it is what you see. Is the further you can see. If you conceive a plane like a cardboard passing through your eyes and going all the way to infinity, parallel to the floor, that defines your horizon. Now, if you look straight up, and which means if you allow a perpendicular line, a line that makes a 90 degrees angle with the floor, going all the way to to straight up, to infinite, pretty much straight up, it defines a point in the sky called the zenith. So zenith, between the zenith and horizon, you have basically a 90 degrees angle, a 90 degrees angle. Now, the Earth has a north and a southern pole, and that's what you can see in this picture here. So let's say if you draw Earth, right, and Earth rotates around an axis of rotation, and the point where this hypothetical axis of rotation crosses Earth, and the north part defines the north pole, and the southern pole and the southern part, and Earth just go around this way. Now, in the very middle of uh, this sphere, we define this, the equator, and the equator is, in the case of Earth, is a circle that happens to be perpendicular to this axis of rotation. Now, let's go back to the concept of celestial sphere. If you take this axis of rotation, which is hypothetical, and extend out to infinitive in such a way that, well, it crosses this hypothetical celestial sphere, it would define the so-called north celestial pole and the south celestial pole. And here, what you're seeing over here is Earth tilted with respect to um, this zenith point. So the zenith point, here's you, if you go back to the previous picture, right? So you're standing on some area of our planet, looking up towards your zenith point. Now here's the same person standing on Earth, but this person happened to be at certain latitude. Let's say this person happened to be at certain latitude. Here she is with a sombrero, and her zenith point is in that direction. And see, everything is tilted here, right? That's the zenith point right there, and the north and south celestial pole. Both of them make a very specific angle, which you can see the semi-angle right there. So if you happen to look straight towards north, so this is the north celestial pole. So what is the north celestial pole again? Is the location, north celestial pole, is the location on the celestial sphere that is coinciding with the extension of this axis of rotation, Earth axis of rotation towards this celestial sphere. That's the north celestial pole. And it so happened that a star, which is Polaris, happened to be very much closer to the north celestial pole. It's about 1 degree off that. So let me stop sharing this and show some other software that helps to visualize what's going on. So I have to go back to, so that there you go. So this is a software that displays the night sky, 12:14. This is the local time, right? 12:14, and January 5th, 2007. It displays the sky as it looks like if you were in San Jose. So that's San Jose in the United States. So the sun is, see this letter S, it stands for south, southeast on the right, left hand side, and southwest on the right hand side. I can move around. And look more towards west, or I can look around and look more towards east. But the main point is, if you look up here, where the time is given 12:15, 3, 4, 5 seconds p.m. So the time is ticking in the top command bar that shows not only the date but also the time and the location. So I can, so if you look at the sky, first you don't see stars, you see only the sun. But I can, just to help visualize things, I can get rid of daytime, right? So that's the sun. Imagine the sun has no illumination at all, or imagine that planet Earth has no atmosphere, and so the sunlight is not as spread, is not as scattered, and then we can see stars during daytime. So what I'm trying to show is this. Well, we are looking straight towards south, right? South is right here, and it doesn't seem that the sun or the stars are moving at all, although the time is changing. As you can see now, it's 12:16. So what I'm going to do, I'm going to speed up the rate in which the time changes. So instead of changing 1 second every second, now the time is going to flow several minutes every second. And if you allow that to happen, see what comes about. That's the moon over here. The moon is coming up. So we are facing south. We are in San Jose facing south. And the time now is going wild. As you can see, it's 8:30 basically. But what we see is slowly and surely and in a very predictable way, stars happen to be rising in the eastern part of the sky, and they seem to be going down below horizons. Here's our horizon. Remember the concept of horizon that I mentioned before. So the star seems to be going below horizon later on. So this apparent motion of stars, this apparent motion of sun, the apparent motion of, let also allow for planets. I'm sorry, click the wrong one. Planets and moon. So planets, the moon, the stars, they apparently rise in the eastern sky, which means by rising, they mean they appear to come out from below horizon up to a position above horizon, and then they seem to cross the maximum height, the maximum altitude, and the altitude is an angle, is the elevation of the star in respect to horizon. So they reach maximum altitude. See, the sun is going to reach the maximum elevation with respect to the horizon when it crosses due south, and then it sets, in the western sky. This apparent motion of stars, planets, and the sun and the moon from east to est or east to west is called daily or diurnal motion. Daily or diurnal motion. And what is exactly causing daily or diurnal motion? What causes daily or diurnal motion is Earth rotation on its axis. So let me see if I can stop this for a while. And go back to some paper that I can write. Right here. So Earth, let me put Earth. Let me just indicate the sun by its rays. So imagine the sun is to the left, right? And I have Earth axis of rotation. This is north. This is pretty much north pole, and we are looking down on the sun and Earth system as if we were standing on the north. So as you look down on the system, Earth, let's place somebody here with a sombrero right below the sun, which means for this person that sits in the equator, this person is pretty much close to noon because the sun is high up in the sky. So as Earth rotates in the sky, 6 hours later, this person is somewhere here. This is noon. This is 6 p.m. 6 p.m. And then 6 hours later, more or less, this person has to be at midnight. Midnight. Oops. Midnight. Because Earth spins around its axis of rotation in a counterclockwise way, as seen by somebody standing north. Now, 6 hours later, from midnight, we are, or that person is in the 6 a.m. clock or local clock. So Earth rotates in a counterclockwise way with respect to a person that happened to be standing north looking down on the solar system. So what we just saw in the Starry Night software as being stars rising in the east and set in the west, this is because Earth itself rotates in the space from west to east, from west to east. And this west to east rotation in the sky give us the impression that the sky itself, with the stars, with the planets, with the sun and the moon, are the ones that circulate around us from east to west. So going back to the Starry Night software, this motion, which looks like a clockwise motion from east to west, is the result of what? Our planet Earth moving and spinning in the space from the western sky towards the eastern sky. And then we see this motion going on, this progression going on an hourly basis. So if you go to your textbook, the authors, they do a simple calculation which indicates that in about 1 hour, because Earth spins 360 degrees in a day, so 360 degrees in 24 hours, it implies that every hour the sky seems to be moving from east to west in about 15 degrees. 15 degrees. And 15 degrees is if you make your arm straight and make a fist with it, so the fist projects in the sky 10 degrees. So any object in the sky is going to be moving from east to west about a fist and a half, 15 degrees. Well, look at what I'm going to do. I'm going to now face north. When I face north, and that explains one of the pictures that you have in your book, when you face north, there is some star. I mean, you see the stars going around as a result of Earth rotation around a point that's Polaris. See this point right here, Polaris? Polaris is a star that happened to be, by coincidence, very much near the North Celestial Pole. And then what we see is the appearance of the stars just going around this imaginary point called North Celestial Pole, and Polaris happened to be near it. And then again, this is the result of Earth rotation, or Earth spinning around its axis of rotation. Okay. Now that's the first basic motion that Earth is subjected to. So let me stop this now. Go back to our original condition, and now let's explore a second motion, and that is Earth revolution around the Sun. So by Earth revolution around the Sun, let me go back to our PowerPoint. Right here. So in this diagram, it shows the Sun in the center and Earth going around the Sun as it goes. Let me see if I can change color. Can I change color here? Let me do that. I have to learn how to change color. I don't know which one of those. Replace, insert text, text comment. Let's just erase. I don't know. So it would be nice to have a different color than black to contrast with the black background. It's not this. Well, I figure out. But anyway, so look at this. Imagine we are on Earth, and so Earth, in addition to these spinning or rotation, which we just explored, there is a second motion, and that is Earth revolution around the Sun. See, revolution is a word different from rotation. So if you were to describe exactly what happened, Earth goes around the sun like this. So it's spinning, but also progressing around the sun. And it does so about 365 spins over the period of 1 year. See that? It makes a funny rotation. Huh? So let's say somebody facing the sun right now, 6 hours later, when Earth is more ahead in its orbit, is going to be here and then there and then there as Earth progresses. Does that make sense? So Earth revolution around the sun make us, let's say, at midnight. So midnight implies that somebody is facing the celestial sphere in this position right here, right? In between Sagittarius and Capricornus. But let's say a few months later, when Earth is somewhere here, when Earth is here, at midnight, the constellation that is going to be crossing the celestial sphere in the highest position in the sky is one between Aquarius and Pisces. And then when Earth happens to be here, what is the constellation that happened to be visible in the sky at midnight? It's Cancer. And then when Earth happened to be in this location right here, which constellation is visible in the sky at midnight? Virgo. So basically, Earth revolution around the sun lead us to see different constellations in the night sky at midnight. In other words, if you go outside at 9 p.m. and then you observe nice constellation in the sky, 3 months from now at 9 p.m., the sky will have a different group of constellations. And that is because Earth revolves around the sun. So let's see how this play out in the Starry Night software. So for that, let's again get rid of daylight. And I'm going to add the ecliptic. And the ecliptic is one of these lines that defines the sun position in the sky all through the year. It's also the name of Earth plane of rotation. Let me bring planets and the moon. There you go. So that's where the planet Mercury, Saturn, Venus, and Mars are. And we are 12:30 p.m. on January 2017. And look what I'm going to do. Let's make 12:30. Let's freeze the time. Okay, freeze the time. And what I'm going to do, I'm going to go 1 day five days at a time. So 12:30 p.m. Oops. There you go. 12:30 p.m. And I'm gonna go ahead 5 days now, and another 5 days at 12:30 p.m. and another 5 days. So see what happening. Look at the stars first. Look at the stars first. Let me give some labels for some constellations. Okay, so now we have Sagittarius, we have Aquarius, Capricorns. So the sun is in Capricorns, and let me go 5 days at a time. See what happened with the constellations? So 5 days at a time, the sun seems to be moving towards east, or better saying, the constellation seems to be moving towards west. Now Taurus is approaching. Look, this Taurus is approaching, and which means the time is the same, 12:30, right? But the days are going forward every 5 days. So this second motion that I'm exploring with the software is one that arises as a result of Earth going around the sun, and so that every 10 days or every 15 days or more so every month, you see different sets of constellations in the sky because Earth is revolving around the sun. So the sun, in respect to a certain star in the background, will be back to that same position exactly 1 year after. And let me show you this right here. So let's place the sun right now. I see the sun in Aquarius. The sun is in Aquarius, right? Which day is that? February 24. So February 24, 2017. How about that 2018? See? The sun is back to the same position. 2019, the sun is back to the same position. So the year, the definition of year or tropical year is, in fact, is a time defined by the sun being in that same position in the sky after a period of what we call 1 year. I know time is a complicated issue, and our book does discuss the subject. It gives some nice introduction to the subject, and I will briefly review if you ask me to. But it's a subject that requires some diversion, and I don't want to do it now. But that is the second major motion. So the third one is precession. Precession is a motion that can only be measured. In fact, it was measured by Hipparchus after he compared data for more than 100 years of data. And then he realized the North Celestial Pole, or the star, the constellation in the North Celestial Pole, was shifting. And then he concluded that was the result of precession. So precession is this third major motion, and it's caused by the combined gravitational pull of Earth and the Sun, or of the Sun and Moon on Earth's equatorial bulge, and then the North Celestial Pole precesses. So I can indicate this with the software, and the way I would do is this. Okay, the Sun is in Aquarius in February 24, 2019 of our time, CE. But if I go to BC, the Sun is not in Aquarius anymore at that time. The Sun is in Pisces. For instance, at that time, if you go to March 21st, the Sun was in Aries. And that is the traditional. So if somebody is born in March 21st, they say, oh, you are in Aries because of astrology. So astrology was a system developed in Mesopotamia at about the time the Sun was in Aries in March 21st. But if you go to our time, the Sun is not in Aries anymore. It's in Pisces. It's in a different constellation in March 21st, right? And it's going to be in Aquarius in about 2,000 years in the future. So this precession is one of the main reasons that is enough to debunk astrology as some sort of a scientific guideline for life. So astrology is more like a curiosity, or you can approach astrology as a religion, a religion belief. You don't need to, you don't care for evidence, right? So you just believe, and then you pave your life according to astrology. But there is no scientific basis on it. It was pretty much invented in ancient Mesopotamia about 4,000 years ago, and there is not a supporting basis for it. So this is the third motion that Earth is subjected to. And now our book also advances further, and let me go back now to this our book. Sorry, I have to go back and forth because I can't share my entire screen. And now we have the introduction of how ancient astronomers and philosophers start to measure these different motions in the sky and try to make a world view of the universe, right? So the first world view of the universe that became formalized is the so-called geocentric worldview, which is pretty much based on the fact that we are sitting on Earth and we have this apparent motion of stars and the sun and the moon rising in the eastern sky and setting in the western sky, and we now call diurnal motion. And we know it's because of Earth rotating or spinning around its axis of rotation, but 4,000 years ago they didn't know. And for all purposes, it seems that the stars and the sun and the moon are in fact the one going around us. And in ancient Mesopotamia, if you study a little bit of the history, before astrology had been invented, the Mesopotamian had invented gods for basically everything. Gods for the rivers, God for the trees, God for plantations, God for every single process. And astrology hadn't been invented yet, but then they start observing that some things happen in the sky that were unusual, like the moon is setting, a new moon is setting, and the new moon is covered with clouds. That means an omen. It means something, and then they came up with an interpretation for that. Or like suddenly there is a storm right in the moment that is pretty much close to one of the eclipses, and that becomes an omen, like the gods are trying to communicate something to the mortals. So astrology start to be developed when they project their gods and their belief systems onto the stars, and then they realize that some stars, including the sun and the moon as stars, sun is a star but not the moon, moon is a satellite, is a natural satellite that goes around Earth. They note that 5 other stars happen to defy the apparent motion of all the other stars. And now we call these stars planets. And they are Mercury, Venus, Mars, Jupiter, and Saturn. So these 5 planets, which for all purposes look like stars, they have independent motion in the sky and does not match the natural global motion of planets in general. Let me go back to the Starry Night software so I can show that. Oh, I think I deleted. Okay, wait a second. I'm reading the Starry Night again. Here. Okay, so let me do that. Here's this the Starry Night software. I'm going to hide daylight. I'm going to bring the ecliptic. And what I'm going to do, also going to label planets and moons so you know what they are. And let's make an exercise, and that is, imagine if we can get out of Earth and look in a given sky position that is coinciding with, let me get it, January, February. There you go, I like this sky.
Alert from System UI server.
There you go. See this constellation right here? This is Taurus, that's Pleiades, that's Orion right there. So imagine we keep staring at Pleiades, Taurus, and Orion in the space. So we are now astronauts, and we get out of Earth and we look at that sky region. And what we see is some objects, the sun for sure, and the planets seem to be moving and wandering with respect to these so-called fixed stars. And you see the time is going by, right? And now I'm going to speed this up. So these wonders later on became associated with planets, and now we know why this is happening. Is because planets are close to us, first of all. Planets go around the sun, second of all. And the stars are very far away. So although in the daylight diurnal motion, we see, let's go back to the daylight diurnal motion. In the daylight diurnal motion, we see every single star, objects, planets going from east to west, and that's what I'm showing now. But if you fix a particular star configuration or stellar configuration and keep observing that, you're going to see the planets passing by, in most of the cases, from west to east. And we call this motion, as we saw previously, prograde motion. Prograde motion. So if we now try to explain prograde motion in a sun-centered system, it's called heliocentric system, it's because planets, the inner planets, they go around the sun with a speed that's larger than the speed of planets that are further out. So if you look at this planet depicted here closer to the sun, going to points A, B, C, D, and E. It's right here, A, B, C, D, and E. The corresponding position of the planet in the further away orbit, let's say the inner planet is Earth and the outer planet is Mars, let's say. So we are going to see Mars in projection with respect to the background stars appearing to move from west to east in what we call prograde motion. But when planet Earth overcomes Mars exactly at this position, and we call this when there is a the Mars is crossing the highest point in the sky at midnight in conjunction. So when Earth passes that point, we see Mars kind of going behind. Mars goes in retrograde motion. Apparently, Mars goes from east to west with respect of the background stars. And then after, on a given position, we see Mars prograding again. So progression and retrogression motion was first explained within the framework of geocentric worldview, Ptolemaic worldview, Earth in the center. So how this Earth-centered worldview explain prograde and retrograde motion? Well, it was a great model. In fact, it could reproduce some of the observable features. And there was, let me explain the model first. So Earth is in the center of the universe, and the planets seems to go around Earth, not in a circular orbit, but in epicycles like this, right? Which means the planet orbits a point, and this point is the one that goes around Earth, which means the planet itself goes around that orbit called deferent in an orbit that we call epicycle. It's a complicated cosmological system, no question, but it works. So when planet Mars was retrograding right here, we see Mars brighter because it's closer to Earth, and that is in fact observable. And when Mars was prograding, Mars seems to be less bright because it was further out. So this model, the geocentric worldview, was good enough to explain what we observed, and in fact was pretty much alive for a good 1,000 years, up to when Copernicus brought his geocentric worldview, a heliocentric worldview, helios, the sun in the center, and it wouldn't explain as well the motion of the planetary motion, especially for Mars, and this was only resolved later when, this is Copernicus, later when Kepler brought the laws of planetary motion, the 3 laws of Kepler's, which indicate planets going around the sun not in circular orbits but in elliptical orbits. And then pretty much that's the birth of modern astronomy, if you will. Now, very important in our quest of modern astronomy is Galileo Galilei. He brought a revolution in our understanding of astronomy because he started testing all the models, all the suggestions he made. Okay. So basically, I would like to emphasize these 3 basic motions in sky objects. Please email me with any questions you might have. If you wanted me to upload explanations to any specific issues, please do so, and I will be happy to do that. And you guys have any question? I have another student there, Evienne Lu. Any questions?
Questions?
Yeah. No question?
No question.
Okay, all right. That's easy. Okie dokie. And you guys have started, okay, let me start taping because now I will be talking